Building an inductor can be quite a tricky process, especially if you don't know these 10 tips. So, in this video, I'm building an inductor from scratch, while also explaining the theory behind it. First of all, you need to know your enemy. What's inductance? Really, here is one simple fact. Everything has inductance. This copper wire, this brass plate, even this aluminum part. The inductance is very small, sure, but it's still there. So, as a physical quantity, inductance just shows how good a component is at storing energy in the form of a magnetic field for a given current. And here is the fun part. Inductance gives materials very interesting property, the ability to oppose change in current, something similar to inertia. In other words, the current through an inductor cannot change instantaneously. The inductor just resists that change by inducing an opposing voltage, according to Faraday's law of induction. This basically means that when a constant voltage is applied to an inductor, the current through it will change linearly over time, unlike a resistor, where the current surges almost instantly. Due to these properties, inductors are used as energy storage elements in switched-mode power supplies, filters, and many other applications. The problem is that the inductance of a single piece of metal is usually too low to be useful. That's why inductors are made with lots of copper turns. Each turn contributes to the magnetic field, making it stronger. Let's take an example. Here I have 10 turns of copper with some inductance. Now I add 10 more turns and measure it again. The inductance increases by about 4 times. Why not 2 times but 4? That's because the inductance of a coil is quadratically dependent on the number of turns. By increasing the number of turns 2 times, the magnetic flux increases 2 times. But now that flux passes through 20 turns, not 10. So the flux linkage increases as well. Put one formula into another and here you go, a 4 times increase in stored energy. However, even that might not be enough, because the initial inductance of several turns is quite small. So, to really increase stored energy, it's time to bring some modern technology. Well, not so modern actually. Back in the 1930s, some Japanese researchers at the Tokyo Institute of Technology developed soft ferrites made from iron oxide. Later, these became commercially available through TDK Corporation, which by the way still exists and makes magnetic cores. And yes, I also use them. You remember, one copper turn without a core gives a negligible inductance, but with a core it's way higher. In fact, it's mu times higher, where mu is the relative permeability of the core. So mu basically shows how many times stronger the magnetic field is inside that material compared to air. By using a material with a high mu, the magnetic field becomes mu times stronger, and the energy stored is mu times higher than without it. Now combine that with multiple copper turns and oof, that's a very nice multiplier. But obviously nothing in electronics comes without trade-offs. Magnetic materials cost money. They also increase losses, especially at high frequencies. And the most important issue, saturation. On the other hand, when no core is used, what's called an air core inductor, there is no saturation problem and no core losses. So to sum up, there are different core materials with different properties. Only some of them are listed in the table here. But I just want to show you a simple experiment with only 2 materials. Here I've got a laminated steel core, which is usually used for low frequency applications. If I measure its inductance at low frequency, the value is quite high, but at high frequency it becomes very small. Why is that? Because the magnetic dipoles inside it are slow. They are like a turtle compared to ferrite, which is a cheetah. A turtle can move fast enough to handle 50 Hz, but once it has to deal with hundreds of kHz, it just can't. In contrast, ferrite has dipoles that can easily reorient at frequencies of hundreds of kHz. That's why its measured inductance at high frequency is still very high. Choosing a core shape is also a very crucial part of an inductor design. The number of core shapes available on the market is a little bit overwhelming, actually. But here is a good rule of thumb. For lowest EMI, go with a toroid, pot or RM core. For high power applications, U or E cores are the way to go. For small RF or precision filters, Pod cores and RM cores are usually the best. And for ease of manufacturing, E cores or drum cores are usually good. For example, I'm building a power inductor for switch mode power supply, which I will be winding manually, so in my case I'm going with E cores. Previously I said that one of the most important magnetic material parameters is its saturation flux density, or BS. When the material reaches this point, it gets saturated. But what does saturation actually mean? Basically, when a constant voltage is applied to an inductor, the current through it increases linearly, according to simple formula. While the current is increasing linearly, the magnetic dipoles inside the material rotate in the direction of the applied field. But at some point, all of them are fully aligned with the field. At this moment, the material is saturated. Once saturated, the permeability of the material drops dramatically. In switched mode power supplies, this leads to a current spike in the inductor, which will most likely burn the power switches, unless there is a current protection. So if I want to calculate peak flux density for the specified current for my inductor, I just grab some parameters from the datasheet, throw them into a simple formula and get the result. But obviously I'm not happy with the result. The inductor saturates at a pretty low current. I need much higher current flowing through it. So how do I increase peak current without saturating an inductor? The easiest way is usually to add an air gap. An air gap actually reduces the core effective permeability significantly, but in return it allows much higher current to flow without saturation. Some cores are sold with pre-manufactured air gaps. In that case, the effective permeability is listed right in the datasheet and can be used in the same formula I showed earlier. For E cores, air gap is usually made in the center leg, because the copper windings are wrapped around the gap and the external magnetic field is minimal, meaning that EMI stays low. Unfortunately, I didn't have the option to grind a proper gap in the middle leg. I don't have a bench grinder, so I had to insert some separators between the core halves to create a gap. But here is the important part. Even though the physical gap is only 2 mm, it actually counts as 4 mm. 2 mm in the middle leg plus 2 mm in the side legs. That gives me an effective permeability of around 50. How did I get that number? From a free software called Ferrite Magnetic Design Tool by TDK. You just select a core size, material and air gap value, and application spits out the effective permeability, along with lots of other parameters like saturation, inductance, number of turns, etc. When it comes to core size, bigger means more power stored before saturation. You can see this in the formula. The core cross-sectional area and magnetic path lengths are in the denominator. So if I take two identical cores instead of one and keep the number of turns, peak current and air gap the same, the inductance just doubles, but the peak flux density BS doesn't change. That's exactly what I did, but instead of using two cores, I used 4 identical pieces. You might ask, why not just buy a bigger core? That would have been easier. Actually, that's true, but I already had these, so why buy when I can reuse? In my design, I took 4 E65 core pieces, glued them to an aluminum substrate, did the same with another 4 pieces. Then I added separators to create the air gap I needed. Then simply clamped the two halves together with threaded rods. If you're wondering where I got those nice CNC machined aluminum parts, they actually came from the sponsor of today's video, PCBWay. PCBWay is a company that can manufacture almost any part you might need for your project. They offer CNC machining, 3D printing, laser cutting, injection molding, painting, sanding, and many other services. But the best part is that along with mechanical parts, you can also order high-quality PCBs. This basically means that from one place, in one package, you can get everything you need to build almost any project you can imagine, which is extremely nice. The ordering process is quick and intuitive through the PCBWay website, where you can get a price quote for your parts in just a few minutes. So what else to say? Go and check PCBWay services. The reference link is in the description. Of course, I almost forgot the most important part, the windings. I wound them around the 3D printed plastic frame. Based on my calculations, I need 22 turns to get around 450 microhenry. So now the question is, What wire should I use to wind this inductor? Ideally, copper should fill as much of the winding window as possible. That keeps the inductor small and minimizes parasitic resistance, reducing ohmic losses and improving efficiency. On the other hand, the current density in the wire must not exceed its limits due to overheating. Obviously, a thin wire can't carry hundreds of amps. So, what should the current density be? Actually, it varies depending on the application, RMS current and type of cooling. Usually for natural convection, the number is roughly 28 amps per millimeter square. Of course, if forced air cooling is used, like fans, number is higher, but these are just rough reference values. In real design, testing is needed to ensure the inductor does not exceed its maximum temperature. By the way, speaking about temperature, here is the interesting fact not everyone knows. Ferrites actually perform much better when heated a bit, up to around 90 degrees Celsius. So if you want extreme efficiency, you can just abuse this feature by letting your inductor run at that temperature and do not cool it down that much. Another pain in the ass is the skin and proximity effects. The easiest way to fix both of them is to use a Leeds wire, which is made of many thin insulated strands twisted together. Obviously, to maximize window feel, rectangular wire or copper foil is often used in low-frequency applications, while square Leeds wire is used at higher frequencies. What are the drawbacks? Well, Leeds wire is very expensive, it's harder to wind and harder to solder. Now here is the very important detail. Which direction should you wind the inductor? If you're in the north hemisphere, you should wind clockwise. In the south, anti-clockwise, to align with the Earth's magnetic field. I'm joking, obviously. It doesn't matter if there is only one winding, of course, and it's not magnetically coupled with anything. Just make it as clean and neat as possible. As one guy once said, things that look good usually work good. During the winding process, I try to keep the wire under tension, so the winds lay down close to each other and close to the plastic. Eventually, at the end, I managed to fit one more turn on the first layer, ending up with 23 turns instead of 22. That should theoretically increase my inductance to around 490 microhenries. The number is still approximate, because like with everything in electronics, magnetic materials also have tolerances. Nobody guarantees that the core has the exact permeability specified in the datasheet, but since all the cores are from the same box, it shouldn't vary that much from core to core. A real pain in the ass, however, is thinning the Leeds wire, because it has lots of strands. Each strand is isolated, so the temperature must be quite high to burn off that insulation. But anyway, did I manage to get the inductance I actually calculated? Well, it's close enough. And the nice part is that the difference between inductors is less than 1%, which is not that bad, considering manual assembling process. It's actually impossible to show every formula and explain every detail in a YouTube video. That's what books are for. I will list a few that are very useful, covering inductors and transformers design step by step, including optimization methods and the underlying magnetism principles. So I hope this video was somehow useful for you. If yes, please like and subscribe. And check out my other videos, they are pretty nice. Love you, bye.